One of the things that you and I share is an intense curiosity about the universe and its fundamental aspects. And what's interesting, I'm interested in the first galaxies in the universe. You're interested in the nature of matter and energy in the universe. In my work on understanding how the first galaxies form, dark matter is what clusters to form the first galaxies in the first place. And if the dark matter isn't exactly what we think it is, then those first galaxies will form at a different time in a different way. You come at it from a completely different point of view.
Yeah, in my case, the objective is to create dark matter in the laboratory and have instruments that then detect dark matter after it is created and be able to study it in detail in the laboratory. And so the NSF-funded LIGO laboratory is a set of 2 instruments designed to detect gravitational waves from the universe. One of the grand challenges identified by the astronomy and particle physics communities, and therefore funded by the NSF, is multi-messenger astronomy. And that fits into our larger picture here via multiple instruments needing to bring their data to the compute engine and analyzing it and reconstructing it and so forth. And one of the most interesting recent examples is when gravitational waves get correlated to neutrinos, get correlated to electromagnetic waves, and a coherent picture emerges for the science. Comet is a watershed moment for us because it's the first fully integrated high-performance computing system that we've ever had. Traditionally, high-performance computing systems were so complex and impossible to use that only the geeks to the nth power were capable of actually making scientific use of them.
By that definition, I'm a geek because I've been using supercomputers for 40 years.
Exactly.
No, seriously, we have broken down the barriers.
For hundreds of years, all you needed to do research was a library. Now, in most disciplines, it is unthinkable to do research without research computing.